much. Thank you so much, Biju. Thank you so much, all the students who have put this together, and I'm really honored to be a part of your fact series. I think this is absolutely fascinating. I've had a look at the different topics you've been through already, and I am so glad today to be able to bring to you the glaciers, and you will see I'm absolutely passionate about my field of study. And today it is my pleasure to take you with me on my expeditions. And we're going to travel to two places that are very, very dear to me. One of them is Greenland, and the other one of them is Antarctica. So can you see my screen right now? I guess it's working okay. Great. So my passion for glaciology didn't come by chance or randomly. I'm actually originally from the French Alps, and this is where I'm speaking to you from right now. So this is me probably a good 15, 20 years ago. I discovered this passion for the mountains. I loved hiking, climbing, mountaineering, whatever excuse I could find to be in the mountains, I would take it and I would run to the mountains. And so very gradually, I started to become more and more familiar with high altitude environments, with the glaciers. And actually one day, a mountain guide told me that I could be paid to study glaciers. And I was like, really? This is real? And he said, yeah, people who study glaciers are called glaciologists. And since then, this has been my target. This has been what I wanted to do for my whole life. So the very first glacier that I've studied is this glacier in the Swiss Alps. It is called the Glacier du Trien. And this is what the glacier looked like a very long time ago, so more than 130 years ago. And this is what the glacier looked like when I studied it in 2010. So this goes to show you that glaciers are very active, and glaciers can react to climate changes very rapidly. So as you know, we're going to be talking about glaciers a whole lot during this talk. And I thought it would be good to start from the very beginning. And I really want to share my secret recipe to make a glacier with you. It's not very complicated, as you will see. All you need is to be in a very cold place and to have a huge amount of time on your hands. So for example, if you're lucky to be in the Himalayas and if you live super high up on a mountain, you will get snowfalls during the wet seasons, and eventually the snow layers will accumulate year after year. And the snow will not completely melt during the dry season, during the summer, because you live in a place that is cold enough. And so year after year, you will get these snow layers that keep on accumulating one on top of another one. And eventually this whole cake of layers of snow will become so heavy that the old snow layers will become crushed by the weight of the younger snow layers on top. And this is how you get glacier ice. As you can see, it's not complicated at all. What I find absolutely fascinating about glaciers is that they all move. They all have different behaviors. Some move very rapidly, some move very slowly. And the reason is that simply they're so big, so heavy, so thick that gravity is making them flow, is making them move. So to illustrate the motion of glaciers, I'm going to show you this, which is probably closer to you than to me. This is the landscape around Mount Everest. Mount Everest is that mountain that is on the top left of the screen, the darkest mountain. And as you can see, there is a whole lot of white on this picture. Most of it is glaciers. And especially there is a big glacier in the middle of the image. There's a very large tongue coming down from Mount Everest. And this is the Kumbu Glacier. And to illustrate the motion of the Kumbu Glacier, I'm going to show you this time lapse that takes a picture every day of the glacier. And putting the pictures together, you see the motion of the glacier accelerated. And this is a glacier that moves up to 2 to 3 meters per day. So here we're rewinding the video. The glacier is not going up the mountain. It would be great, but I've never seen that. So the glacier is always coming down the mountain. And this is also very important mountaineering routes for all the climbers that try to go to the top of Mount Everest. They actually have to cross this glacier. So as you can see, there is quite a lot of action taking place when we start looking at glaciers. So there are quite a large number of glaciers in the world. I mean, every time when my parents, talk to me about my job, they say, oh, come on, why did you decide to study glaciers? Like, there are so few, but actually there are 200,000 glaciers in the world. And what we call glaciers is kind of the smallest unit in terms of ice masses on Earth. So you have glaciers. Glaciers is typically what you find in the Himalayas, what you find in the Alps, in Alaska, what you find all along the Andes, in Scandinavia or in Iceland. If you go up one class size, you have the ice fields. So for example, on the archipelago of Svalbard, I think I can put a little laser pointer. On the archipelago of Svalbard, we start to have ice fields. Then if we go one class up, it is the ice caps. So we have some ice caps in Iceland or in Patagonia, for example. And the largest size of ice masses on Earth are the ice sheets. And this is what I will be telling you about today. So we have two ice sheets in the world. It's not very complicated. We have Greenland in the north. And then the mothership, the biggest one of all, we have Antarctica. So before we go any further and dive into my expeditions, I wanted to really insist on the fact that glaciers, ice fields, ice caps, ice sheets matter. They matter enormously. And we're going to quickly flick through the reasons why. And this is yet another glacier from my region. This is the largest French glacier. It doesn't look like much at all these days. It's called the Sea of Ice, which is a very romantic name. But basically glaciers, as you can see, they change a lot in size and volume because they react very quickly to climate changes. So if they get more snow, if it gets a bit colder, glaciers will start to become bigger and bigger. But the opposite can also come true. If glaciers receive a lot less snow and the temperatures increase, the glaciers will start retreating. And typically, of course, this is what we're seeing at the moment. This is also true at the third pole in the Himalayas. This is what we call the third pole in glaciology. And the glaciers of the Himalayas are so important because they bring a lot of fresh water to a very large part of humanity. And when we look at projections, when we look at the future of these glaciers in the Himalayas, well, it's not good news all around, unfortunately. Depending on the trajectory we decide to take in the next few months, in the next few years, we could lose up to 50 to 70% of the glaciers of the Himalayas by the end of the century. And this has tremendous consequences that you're more aware of than me, for sure. And the consequences are all related to, again, to fresh water. We know that the fresh water coming from glaciers can play a very, very big part in the discharge of some of the biggest rivers on Earth. And this is what this complicated figure is trying to show, is the proportion of fresh water coming from the glaciers that goes into the biggest rivers on Earth. And if you look at Indus, for example, more than 30% of the water in Indus comes from glaciers. So you can understand that actually, yes, these glaciers matter a lot for this and everywhere else on Earth where we have glaciers. Glaciers and ice sheets are also very important because they hold these very precious and beautiful climate archives. I know this was one of your questions. Basically, when you take a sample of ice, when you collect an ice core, and you look at this ice core in great details, you will see millions and billions of bubbles of air. And these bubbles of air are basically trapped in the ice, and they became trapped in the ice when the snow layers were accumulating on top of each other on the upper part of the glacier or in the center of the ice sheet. And by analyzing the chemistry of these air bubbles, you can reconstruct climate over very long periods of time. So I have some colleagues who are on the hunt for ice in Antarctica that is 1 or 1.2 million years old. So glaciers have been helping us to understand the abnormality of the change in climate that we're having currently. Glaciers are also very important for tourism. Of course, people go to the Himalayas to see glaciers. People go to the Alps to see some glaciers. In the Alps here, people ski on glaciers during the summer. It doesn't look very attractive, but this is what people do. Glaciers also matter a lot because they're typically white, and by their color, they're able to reflect a lot of the solar radiation we get. And this has been true for a very long time, but because glaciers are melting and thawing so much faster than before, glaciers are getting darker and darker every year. So to counteract this, in the Alps, what people do is that they cover glaciers with white sheets. I mean, how crazy is that, right? It is very effective. As you can see on this picture, the parts of the glacier that are sticking out, these were the portions that were covered by the white sheets, while the rest of the glacier melts much more readily. But this is not sustainable, as you can imagine. But then, the most important reason why we study glaciers and ice sheets today is because of sea level rise. When temperatures increase, glaciers, ice caps, ice fields, ice sheets melt. But also, for the glaciers and the ice sheets that go all the way to sea level, they can actually dump some massive bits of ice directly into the oceans. And when we look at Greenland and Antarctica, this is the main process by which the ice sheets contribute to sea level rise. So enough of theory, time to head to the field. And my first big polar expedition, before even going to Svalbard, before even meeting Biju and Tina, was actually to go to Greenland. And I was 23 at the time. I was very naive, but I was so excited to travel to Greenland. Greenland is a very important place because it is the largest island on Earth. It is almost completely covered by ice, up to 3 kilometers of ice in some parts. But most importantly, Greenland is in the Arctic. And we do know that the Arctic is currently the place on Earth that is warming the fastest. And the changes in the Arctic are incredible, not in a good way. The Arctic is changing extremely rapidly. And we can explain this pace of change by one thing. Remember, I told you that glaciers are very good at reflecting solar radiations, and they're really good at this. But in the Arctic, we have another type of ice, and this ice is sea ice. Sea ice doesn't form on land like glaciers and ice sheets. Sea ice forms on the ocean, and this is a crust of ice that can be a few meters or several meters thick. And sea ice is always in motion in the Arctic. As you can see, it's moving because it's being pushed by the currents, by the wind. But unfortunately, sea ice is extremely sensitive to changes in water temperature and air temperature. So this big white natural mirror that is covering a huge proportion of the Arctic Ocean is retreating extremely rapidly at the moment. And this is what you can see here on this video, is that, of course, sea ice is expanding during the winter, retreating during the summer, but there is this permanent cover of ice. But year after year, it is retreating more and more every summer. And the retreat of the sea ice, especially in the summer, explains why the Arctic is warming so quickly. So there we are. I was finally going to Greenland after months and months of dreaming about this. And to go to Greenland, to go to the ice sheets of Greenland, we had to take a series of planes that were getting smaller and smaller at every step. And this was the last plane we took to finally get us to our field area. This was the time of April, and April in Greenland is typically spring. So you don't have the lowest temperatures of the winter. You don't have the heat of the summer. I mean, heat, it doesn't get that warm. So we were expecting to get between -10 to -20 degrees Celsius. And from the plane, I mean, it was mind-blowing. We could see all these crevasses. There was white all around us. And eventually the plane landed on the ice sheet. And I remember some of my colleagues were already there. And my colleague Sam opened the door of the plane and told me, Heidi, welcome to hell. And I can tell you, it was hell. As much as I love glaciers and I love ice sheets, this was by far the toughest expedition of my life. What happened is that during the first week of the expedition, we got a cold wave, not a heat wave, a cold wave. And for the entire week, we got temperatures down to -43, -44. And this was terrible. I mean, everything was breaking down. Our bodies were breaking down. Our instruments were breaking down. It was very difficult. But on top of surviving, we still had to do science. And this is what I like about glaciology. It is a challenge. You have to look after yourself, look after your team, but you have to collect some data on top of it. So what did we do in Greenland? Well, what we did mostly is planting, what you can see on this image here. We planted GPSs on the ice sheet. It's not very complicated. We were very interested in measuring the motion of the ice from the top of the ice sheet to the coastlines. Because if ice is moving very, very quickly towards the ocean, well, that means that Greenland is losing more and more ice into the ocean by this process I was telling you about that is called calving, that produces these big icebergs. And we were really interested in knowing how quickly is the ice sheet moving. Is it going faster towards the ocean? Is it going slower? But there is a process that is currently taking place that is making the ice sheet accelerate. We have these lakes that form on the surface of the ice sheet every summer. These lakes come by millions. And eventually, these lakes always find a way to drain. They find a little fracture, a little crack in the ice sheet. And the water, as you can see on this diagram, the water can go all the way to the base of the ice sheet. And this will act like soap. It will lubricate the motion of the ice sheet, making it accelerate towards the ocean. So this is not good news. And guess what is accelerating the formation of these lakes? You've probably had a talk about this already. It is black carbon. It is the pollution that is floating in the atmosphere. It is also dust that come from Greenland or so many other countries. And the fact that Greenland is getting darker, darker every year makes it melt faster. More lakes are forming and these lakes drain through the ice sheet, making it accelerate and contribute even more to sea level rise. And so last year, we saw so many of these lakes forming. This is just a little zoom over one tiny portion of Greenland, but you can see these lakes forming very quickly through the month of June. And we're seeing the same thing happening this year. So what's happening at the moment when we look at the gains in terms of snowfall over Greenland and the losses in terms of calving? Well, Greenland is losing more and more mass every year. And it's losing a lot of mass along the coastlines, along the periphery of the ice sheet, because these are the places that are at low elevation, of course, so they're getting warmer and warmer. But also these are the places where the ice sheet is accelerating the most every year. So at the moment, Greenland is losing a lot more mass than it is being resupplied by from snowfalls. And we say that Greenland is losing these years approximately 300 gigatons of ice. So these are billions of tons of ice. And I know that some people say, oh, this is equivalent to so many swimming pools. This is equivalent to so many elephants. But what I like to show that 300 gigatons is equivalent to all the glaciers of the European Alps. It's not as big as the Himalayas, of course. We have about 3,000 glaciers here in the European Alps. But basically, Greenland is throwing into the ocean the equivalent of all the glaciers of the European Alps every year. So this is really, really impressive. So my expedition in Greenland eventually became a little bit easier after these horrible temperatures at the beginning. It got gradually warmer. We spent an entire month camping on the ice sheet. And after a month, let me tell you, I was ready to go back home, but I was so happy about the data we had collected. But after being in Greenland, I had my eyes on the other ice sheets because I always wanted to go further and further away. And eventually, I got the chance to investigate Antarctica. So why do we focus on Antarctica at the moment while the Arctic is warming extremely rapidly? I mean, Antarctica is so much bigger than Greenland. Why are we so interested in Antarctica? Well, exactly because of this. If the whole of Greenland were to melt, it would increase sea level globally by about 6 to 7 meters. I mean, this is already enormous, right? When we're talking about some places in India, even some places in France, in my country, 6 to 7 meters is already destroying so many cities and coastlines. But when we look at Antarctica, if the whole of Antarctica were to disappear, it would increase sea levels globally by 58 meters. So this is a completely different ball game, and this is one of the main reasons why now most glaciologists are turning their interest towards Antarctica. And Antarctica is paradise for glaciologists. It is an incredible place, the place of all extremes. Antarctica is about 23 times the size of my country. So, I mean, this is just a completely new environment for me. And I got to spend 6 weeks on a certain region of Antarctica, and I learned a huge amount. But let me tell you, it was way easier than Greenland. We got better temperatures. So this is what Antarctica typically looks like in the middle of winter. This is not the time when we went there, but I really wanted to show you this image because we see it very rarely. Antarctica in the winter gets surrounded by this crown of sea ice that is over the ocean. But Antarctica is first and foremost a continent covered by ice. There is up to 4 kilometers of ice in Antarctica. We typically divide Antarctica into different regions. There is the Antarctic Peninsula that is kind of like, if I hold my fist like this, it's kind of like this little notch that is sticking out from Antarctica towards the north. And this is the Antarctic Peninsula. Then we have this beautiful and incredible mountain range called the Transantarctic Mountains that is splitting Antarctica into 2 parts. And we actually give them different names because they behave very differently. There is the West Antarctic Ice Sheet and the East Antarctic Ice Sheet. And the South Pole is somewhere there. So Antarctica, just like its brother further north, Antarctica is also losing more mass than it is gaining. And this took a very long time for scientists to be able to say that with certainty. Because Antarctica is so big, it is very difficult to study it. And it is only thanks to the development of satellite data that we've been able to understand Antarctica as a whole. We've been able to also measure changes regionally. We've been able to say, okay, well, this region is warming faster than another one. And so this is what this little animation is showing you, that some parts of Antarctica are warming extremely rapidly. That is the Antarctic Peninsula, the West Antarctic Ice Sheet, and some parts of the East Antarctic Ice Sheet. But some other portions are also getting colder and accumulating more and more mass every year. But if we make the total of that, the gains and the losses, Antarctica is losing more mass than it is being replenished with. So Antarctica is a very special place because we have ice covering the continents. The ice gets so thick, so heavy, that eventually all of this ice that is over the continent, so this is what I'm showing you in yellow here, the ice will start to float over the ocean. It will not immediately break away in a myriad of icebergs. It will actually start floating. And so this is what I'm showing you here in blue. This is what we call ice shelves. Ice shelves are not sea ice. They're made of continental ice, really big, thick, cold, hard ice that is coming from the continent. These ice shelves can be as big as my country, and they can be extremely thick, easily 800 meters thick to a kilometer thick of ice that is floating over the ocean. And these ice shelves, I'm going to tell you about them now because this is what I went to study in Antarctica. They are extremely important and they matter a lot when it comes to sea level rise. They matter a lot also because 75% of the coastlines of Antarctica are connected to at least one ice shelf. So let me show you a little bit more about what they look like. So this is what ice shelves look like. Typically, it's ice that was grounded, so that was resting on the continent, that will start to float. And usually ice shelves, they can only form in these natural embayments. So they're kind of holding themselves on the sides and they can progress over the ocean. And so they're gradually flowing and floating over the ocean. But what they do also is that they are slowing down the motion of the ice. They are preventing too much ice from the continent to go directly and break up over the ocean. So this is why we call ice shelves basically the guardians of Antarctica. They exert this back stress by holding the sides, by holding onto the coastlines, they're slowing down the motion of ice. Unfortunately, yes, they're floating. So they don't like when air is getting warmer and they don't like when the ocean is getting warmer either. Just like sea ice, they're very, very sensitive to that. The problem is that what we're observing at the moment is that ice shelves are collapsing. They are disintegrating in Antarctica. And this is what I'm going to show you now. So we're going to zoom in on the upper part of the Antarctic Peninsula, on the northernmost part of the Antarctic Peninsula. And all of these portions that look very flat, that are completely white, these are ice shelves. So this was the Larsen A ice shelf, this the Larsen B ice shelf, and I'm going to show you a series of satellite images from 1986 until almost today. And you're going to see what's happening at the moment. That basically these ice shelves are collapsing. They are carving enormous icebergs. They're disappearing year after year. And the problem with that is that all the glaciers that are resting on land, so all these glaciers that are coming from these mountains, there is nothing slowing them down anymore. So guess what? They're moving faster towards the ocean, and this is contributing to sea level rise. Excuse me. So let's go to Antarctica. Finally, let's join my expedition. So I was very lucky right at the end of my PhD to be able to join a team of British glaciologists who were going to investigate the next ice shelf in line on the Antarctic Peninsula. So this was where my little animation that I've just shown you was. But if you continue further south, you have this gigantic ice shelf called the Larsen Sea Ice Shelf. And many people think this is going to be the next one in line to disappear. So this is where we were going to find out. We were going to find out how structurally sound is this ice shelf. What can we find in the ice of the ice shelf? Is it strong enough? Will it resist to further change in climate, to further warming? So this is what we did. The project I joined was called the MIDAS project. MIDAS for Impact of Melt on Ice Shelf Dynamics and Stability. Do not ask me how this acronym was built. I don't know how this came about to be called MIDAS, but anyways. And so it was kind of a group of different British universities. Aberystwyth is where I did my master's degree in glaciology. And we were to spend 6 weeks on the Larsen Sea Ice Shelf. But before that, the Brits, they're not crazy. They're not going to send you right away to Antarctica. First, you have to go through this kind of boot camp in Cambridge that is about a week long to see if you could survive in Antarctica. I mean, not really, but it's definitely a big test. So you're learning to put down fires, you're learning first aid, you're learning how to deal with conflicts within a team. And I found it very, very useful. This was a great exercise. And eventually, the time came to go to Antarctica. So to do that, we took a series of planes to reach the southern tip of South America. So this was Puntas Arenas in South America. And we took one last plane to go to this place on Adelaide Island in Antarctica. So this is Antarctica in the summer. There is basically no sea ice left. And the flight was incredible, as you can imagine. It was between 4 and 5 hours of flying. There was a lot of ocean first, and then we started to see the mountains of the Antarctic Peninsula. And it was just so beautiful. We were all glued to the windows of the plane. When we got there, we actually didn't land on the Larsen Sea Ice Shelf directly. We actually went to a station first because we had to go through some further training. This station, I don't know if you can see it on the image. I can leave you a couple of seconds to guess what the station is. But you might notice that there is one feature that is quite abnormal on this image. It is this thing, this straight line. You rarely have straight lines naturally. This is the runway of the Rodera station. So this is what it looks like. We were the first team of scientists to get there after the winter. So we were going there during the spring. And there was approximately 22 people who had spent the winter there. And it's a pretty hardcore, people spending the winter there. I mean, kudos to them. It's really a big challenge. But we spent about a week at the station. We went through all our equipment to make sure our equipment was working. But also we had a lot of preparations to go through. And luckily, when you do fieldwork with the British Antarctic Survey, they give you mountain guides to help you organizing the logistics, and also a little bit to babysit the scientists, because, I mean, we're sometimes too focused on the science and not focused enough on safety. So we had two amazing mountain guides. Al here, Big Al, that was his name, was one of them. He was incredible. And here he's showing us how to operate the stoves and the lamps to make sure we don't burn the tents down when we do some field work. Here, this is Suzanne, and Suzanne was my tent mate during the expedition. And here what she's rolling is kind of the bed or the bedding. This is what we're going to use to sleep on during the expedition. It's like many layers of foam, fur, blankets, fleece, just to keep us warm. And it was very comfy, I have to say. Eventually, we got the green light to go onto the Larsen Sea Ice Shelf, and we had one last flight, which was about an hour and a half, over the Transantarctic Mountains to go to the Larsen Sea Ice Shelf. And this is what you can see here. Everything is white. I mean, this is Antarctica, but it was absolutely beautiful. Eventually, we landed, and right away, you have to get to work. You have to set up the camp. And as you can see, look at how flat it is, because we're floating. It doesn't look like it, but we're floating over the ocean. And this is what home looked like for 6 weeks. So again, I was sharing with Suzanne here. She's logging on some data. We had a little stove. We had a lamp that was also our heater, but we had not enough fuel to have this on the whole time. So we would turn it on for 15 minutes, turn it off, and freeze all the time, pretty much. But besides that, we had such a good time because we had 6 weeks on the ice shelf. 6 weeks, you know you have time to do everything. You know you're going to have some good weather, some bad weather. So we took the time and we collected the best data ever. So what we were interested in was mostly to know more about the structure of the ice shelf. So to do that, we used a series of different techniques. Here, my colleague Adam is showing this instrument. This is a ground penetrating radar. Perhaps some of you are familiar with this. This is a great technique that sends pulses of radio waves through the ice. And it works a little bit like a sonar. And by trying to look at the time it takes for the waves to come back, and by looking at the polarity of the waves, we can learn a lot about the temperature of the ice, about the density of the ice, and also detect some abnormalities within the ice. So that was a very useful thing. And we were actually dragging it using a snowmobile. So we covered thousands of kilometers with the GPR. We did a lot of snow pits. These don't go as deep, of course, in the ice shelf, but we were really interested in looking at the snowfalls from the winter and trying to see if we could identify melt that took place during the winter. Because at the time, there was no weather stations on the Larsen Sea Ice Shelf. So we were kind of like leading this police investigation to try to reconstruct what had happened the winters before. And what we could see just by digging through the snow from the previous winter, we can see, you see all of this. These are ice lenses, and ice lenses form in the snow only when you have a melt event. So let's say you have snow that has fallen during the winter and it melts a little bit, so it creates a mini pond, and the pond will eventually refreeze, forming this lens of ice. And we couldn't believe it. We couldn't believe that throughout the winter there had been so many melt events. And now we know that actually you can get positive temperatures in the middle of winter, up to 14 degrees Celsius, 14 in the middle of winter. This is stuff we're detecting at the moment. And then one of the other techniques we used was drilling, and this is Bryn, this kind of Welsh Viking. Bryn was the leader of the project, the nicest glaciologist I've ever met. And Bryn was in charge of drilling holes through the ice shelf. And this is a pretty horrible job because to drill holes, we use a pump that is just here, that is throwing hot water, liquid water, of course, through the ice to basically make a hole through the ice. But to have liquid water, we had to melt snow, and we melted snow for days and days and days. And this is what our guide and David here are doing, is melting snow to get enough water to drill. But we were drilling holes not to collect ice cores, but to do the opposite, actually. What we did is that we lowered a camera in the hole to take pictures and do like a negative ice core. And that was very interesting to learn more about the structure of the ice, the density of the ice, and we learned a lot from this technique. And we also put a lot of thermistor strings, so a lot of temperature sensors measuring the temperature of the ice. And they're still there, which is very good. And the last technique we used was seismics, which is a fantastic technique. And to do that, we actually had to hammer the ice shelf as much as we could and as hard as we could to create these artificial earthquakes. And by looking at, again, the propagation of the waves through the ice, we learned a lot about its structure. And so this is our second guide, Bradley Bradders. He had a little bit too much energy, so we tried to make him tired as much as we can by letting him be in charge of the hammer. So what we found during this expedition really surprised us. To be fair, we knew very little about ice shelves, about the structure of ice shelves before going there. But actually, we couldn't believe it when we looked at the data. What we found surprised us so much. I'm going to show you a video that we didn't collect, but that was collected on another ice shelf in Antarctica, but that shows exactly what we found on the Larsen Sea Ice Shelf. They drilled a hole, lowered a GoPro through the hole, and you expect to find good ice, hard ice, but eventually ice shelves always keep surprising you. This is what they found. So I don't know if you can see very clearly because it's a video, but basically it is a lake within the ice shelf. So the lake is not very deep. It's just a few meters down the surface of the ice shelf. But basically, these lakes are created by these ponds that form on the surface of the ice shelf during the winter, during the summer, and eventually they start draining through the ice shelf deeper and deeper every year. So imagine it's like having a block of concrete pretty much with marshmallow in the middle. These ice shelves are threatened by these lakes that are inside of them, that are within the thickness of the ice shelf. And so we published a lot of papers based on these results. And we know there's still a lot more we need to understand on these ice shelves. And at the moment, it appears that the Larsen Sea Ice Shelf is still surviving. It is definitely nested in one of the warmest places of Antarctica. But unfortunately, it is not the only ice shelf. The whole periphery of Antarctica is surrounded by ice shelves, and some are melting extremely rapidly. So this is what this figure is showing, the rate of thickness change in meters per decade, which is a weird unit. But basically in red are ice shelves that are losing more and more of their thickness, and in blue are ice shelves that are gaining thickness. And you can see this big disparity between the peninsula and West Antarctica that are melting very quickly, and East Antarctica that is kind of okay at the moment. But basically, if we lose these ice shelves, it means that the ice from the continent of Antarctica will be able to move much faster towards the ocean, contributing so much faster to sea level rise. So we're keeping a very, very close eye on what's happening to these ice shelves. The reason why today I wanted to tell you about glaciers, about ice sheets and ice shelves is because of what is currently happening. And thank you again for the great introduction you gave to my talk. But glaciers matter. Glaciers matter a lot more because of climate change. And the problem with glaciers and ice sheets is that once they go through a certain threshold in temperature, once they go above that, we go through irreversible changes. And we're often talking about the point of no return or tipping points. And this is what happens for glaciers and ice sheets and ice caps and ice fields. If we go beyond certain temperatures, we will never be able to grow them back. So this is what this diagram is showing. So you have the scale of temperatures at the bottom. If we take all the efforts that the international community is doing, if we take into account everything that the governments have said that they will put forward in the next few years or few decades, we will actually go between 4 to 4.5 degrees by the end of the century. I mean, this is where we're heading at the moment. And this diagram is slightly outdated because of it. But at the moment, we are following the high emission scenario. We are on the worst case scenario trajectory. And that means we will probably be around 4 to 4.5 degrees by the end of the century. And what does that mean in terms of glaciers, in terms of ice sheets, in terms of sea ice? Well, the picture is very clear. If we go even beyond 2 degrees, the West Antarctic ice sheet could be lost if we go beyond 2 degrees. If we go beyond 2 degrees again, we would lose such a big part of our mountain glaciers. If we go beyond 3.5 degrees, we completely lose Arctic sea ice. And there was a paper published a few days ago that said that we will lose summer sea ice in the Arctic by the year 2035. I'm not even talking about the end of the century. So anyways, as I keep moving up, eventually we start to reach the big ice sheets of Greenland and the rest of Antarctica, the East Antarctic ice sheet. And again, if we go beyond certain temperatures, we will not be able to grow them back. We will go through these irreversible changes. So that's something that is very important. Many countries in the world think that we can overshoot our climate targets, go beyond the Paris Accord, go beyond 2 degrees by the end of the century, and then maybe we will be better. We will use better energies during the 22nd century. This doesn't work like that when it comes to glaciers and ice sheets. So I remember that one of your questions was about whether all of these current climate change was natural or was it being emphasized by our activities. And this is what I'm going to show you very, very quickly. This is a very simple curve showing you the changes in temperature globally from 1880 to 2015. So this is kind of the baseline we have. And as you know, temperatures are currently increasing. So is it natural, the changes in temperature? So when we take natural factors into account, so this is the variation in solar activity, these are volcanoes, these are also changes in vegetation, natural changes in vegetation over the planet. This is what we get. Well, basically, if we take all these natural factors into account, and these big dips are actual volcanoes, actually, no, we do not get a warming at the moment. Maybe slightly here at the end, but we do not get such a tremendous warming. When we take our emissions of greenhouse gases, this is what we get. We actually get a warming that is slightly above what we're observing at the moment. But as you can see, it is interesting how closely it is matching the observed changes in temperature. And eventually, if we take everything into account, natural factors, human factors, and we put them together, it matches very closely to what is happening at the moment. So as you can see, we are playing a big part in that. And just a couple of days ago, someone on Twitter published this diagram, which is incredible, which was simply called the last 2,000 years. As you can see, or probably imagine, it is showing changes in temperatures over the past 2,000 years. So this is the average in temperature over the past 2,000 years, cold periods, warmer periods, and here is where we're at the moment. Just to show you how abnormal the change in temperature is over the last 2,000 years. But this is not the only thing I wanted to show you. We do know now that the CO2 increase in the atmosphere is actually unprecedented over the past 2 million years. And to be able to reconstruct the climate over such a long period, we've used ice cores and many other proxies that I'm sure Tina could tell us about also. But just to show you that what is currently happening is unprecedented over a very long period of time. And the only reason why we care so much about the current change in climate is because it is affecting us. And this is why we need to tackle this challenge head on. This is my final slide. I really wanted to give you some hope and some motivation. Because, I mean, if you're like me and you look at glaciers day in, day out, you never receive any good news. They keep on melting faster and faster every day. But spreading awareness on climate change is capital today. It is crucial to be able to make a difference. With the few messages I was able to share with you today, I really hope that you will take these messages back home and try to share them with your friends, with your family, with your colleagues. This is very important. So, of course, glaciers and ice sheets all over the world are melting. Human populations are already being affected by what we're detecting. And what is very important is that it is a choice whether we want to continue to see these glaciers and ice sheets melt or not. This is completely a choice. So what are the solutions? Well, when it comes to glaciers, there is no miracle that we can do. The best solution is actually to try to distance ourselves with fossil fuels as quickly as possible. It is very difficult to do that in some countries more than others, but this is definitely the only solution that will work. Many people are working on geoengineering solutions at the moment to suck CO2 from the atmosphere and put this in the ground. This is not developing fast enough to be able to suck enough CO2 and to put it into the ground and compensate for our current emissions. So let's act, let's make a difference. And with that, I thank you so much for your attention, and I would be super happy to take any questions you might have. Thank you very much. Okay, go ahead. I don't know if how you want to do this, if you want to turn on your video and talk. Otherwise, I have copied the questions you have sent me already. So up to you.
Hello.
Yeah, Joby, go ahead.
I think we have a few questions in the chat box.
Perfect. Okay.
It would be great if you can
address
them.
Okay, ma'am. Can I ask you one question, ma'am?
Yes.
Hello, can you hear me?
Yes, I can hear you. I have been
My name is Abinsha. My name is Abinsha. I didn't happen to see your thing, but I joined later. I have a question, ma'am. We saw different pictures of before and after Corona. I think you also have seen. And do you think did Corona really help to improve climate changes? Any good effects of that?
Thank you. Thank you for your question. This is a very important point. And it's a very timely question as well, because 2 days ago was what we call Overshoot Day. I don't know if you were able to follow that, but it is basically the day on Earth from which we have used all the resources from the planet that the planet is producing for the year, and we start to borrow over more resources from the planet. And the date at which Overshoot Day falls is very indicative of our activities and emissions. Thanks to Corona, the day of Overshoot Day has been moved by 3 weeks. So we've gained or saved 3 weeks compared to usual. And you might say, what? 3 weeks? This is nothing? It is very small. Actually, what we've been able to do during Corona, and they've been locked down all over the place. I remember speaking to Tina, there was a lockdown in India, there was one in France as well. Actually, during lockdown, we were still using a lot of energy. We were still using our phones. We were still perhaps using our computers. We were still cooking. So we were still using a lot of energy. What has probably been decreasing is our mobility. And so we've been able to decrease our emissions by about 5 to 7%, our emissions of CO2,
I think
which is it's a very good thing, but this is not enough. Basically, this is what we should be doing every year from now on. 5 to 7% is what we should be doing to be able to maintain global temperatures below 2 degrees by the end of the century. So imagine the effort this will take to tackle climate change, but we don't have a choice. This is what we'll have to do. Not necessarily lockdown. There are much better solutions than that, such as cleaner energies. But 5 to 7% of CO2 emissions is what the coronavirus actually produced. Yeah.
Okay, ma'am.
So
I have one more question.
Yeah.
Can I ask? As a solution for this call, we are now saying that electric cars will reduce the CO2 emission. But for that also for making electricity, we are also depending on also emitting some sort of
Absolutely.
CO2. So how will you
Yeah.
tackle this?
I completely agree with you. I mean, there's no point using electric cars if your electric car is powered by coal, for example. You know, if you plug in your electric car directly connecting to a coal power plant. I mean, figuratively, but you see what I mean. I think there is not one solution that will apply to the rest of the world. The most important thing first is to be aware of how much energy we're using and to be able to start reducing the amount of energy we're using. This is the first thing. If we do not go through that first step, there is no point looking at other sources of energy. So I think trying to save as much as possible is very important. Trying to be considerate of how much food you're buying, how much food you're wasting perhaps, how much electricity you're using for cooking, all of this is very important. Then, as you said, mobility is a very big one. And mobility releases a huge amount of CO2 emission. And we can definitely find other ways to transport merchandises, to transport people than electric cars. I think it is perhaps a solution in some places where electricity is produced using hydroelectricity, using hydro, for example. So in places like Iceland, where most of the energy is being produced by geothermal activity. But if the electricity in your region is being produced from fossil fuels, then there is it doesn't make any sense to be having electric cars. But there are so many other sources of energy, so many other ways to travel. And in France at the moment, you know what they're trying to do? They're trying to have more trains and to put merchandise on trains. And even though trains are a lot slower than cars or trucks, actually this is a great way to carry materials and people over land. So thank you for your question.
Okay, I also think a good suggestion is utilizing solar power for electric production. That will emit the CO2 emission and etc. Ma'am, I want to talk to you. My battery is so low; it's 12%, so might get off the phone. And I want to tell you that I like to work with you. And currently, I'm looking for a job, but part time I would like to work with you. So any contact you can give me, please put in the chat box so I can
For
take
sure.
it.
Don't hesitate. Yeah, I'll just put my email here. Anyone, if you want to email me, feel free. Up. And thank you for your questions. See you soon. I'll take some other questions from now on. So let me see in the chat box. Whoop, 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 lots of questions. In which journals the results were published? So I think this is probably referring to our work in Antarctica. So we published in Nature for this work. And I have to say that nowadays I'm slowly working more and more in science communication, and I feel very sad when I see journals keeping these important results behind paywalls. I'm all for open access. I'm all for getting these results out to the world. And when I saw that our paper, you had to pay like, I don't know, or to have a subscription to be able to read our paper, this made me very sad. So these big journals are great to put on your CV, but in the end, you know, if they are not open access, I do not see the point of having of publications there. So then what was your inspiration behind this journey? Thank you, Akio, for your question. To me, I think I've always been really attracted by extreme places and places where nobody goes to. And I think Svalbard is one of them for sure. But I've always been tempted to, you know, to look over the hill and to try to see and go further and further. And I mean, when you're a glaciologist, Antarctica really is the holy grail of glaciologists. You always want to go further. And as a woman in glaciology, luckily, I've always worked within teams that didn't care. They didn't care who I was. They were making me carry heavy things. And I really appreciated that in a way that I was always treated as equal as my male counterparts. And of course, glaciology is a very male-dominated field. But, you know, it doesn't matter whether you come from the middle of the Alps or the middle of India or the middle of, let's say, Chile. Anyone can become a glaciologist. And I really, if you're keen to go and travel to these remote environments, I would really recommend you to do so, because you learn so much from seeing these glaciers, from being there. It's been a very humbling experience for sure. Good. Any questions live, or should I keep going through the chat? I can keep going down about the little air bubbles, because this is a fascinating question. It's so fascinating that I've prepared a little slide about this. You see, I was prepared. So let me share my screen again. Up. And if I didn't forget what I was sharing, yes. So ice cores. Let me see. It should be able to, you should see my screen now. Can you see it? Yeah, perfect. So ice cores are fascinating because although it's a piece of ice, you can actually extract a lot of information, not just from the air bubbles, but also from the ice itself. So typically when we collect an ice core, we will split it in lots of different parts because it's very precious. I mean, when we go to Antarctica, sometimes we get like one ice core and you want to make sure you make the most of it. So you will have like the biologist will say, hey, I want a piece of this. Then the guy who is like looking at chemistry will be, oh, what are you talking about? I want the biggest piece. And then the glaciologist will say, oh, keep me a piece of the ice core. So this is what we do. We basically make a little puzzle and we split it into different parts. As you can see, we're very interested in all of this. So archive is basically what we will keep in the lab forever. And this is what we will analyze, the chemistry and the gases. So what we've been able to reconstruct with ice cores has been absolutely exceptional. We've been able to see changes in our climate over hundreds of thousands of years. And this is what I wanted to show you, this from an ice core that was collected in Antarctica, actually probably in the coldest place in Antarctica that is called Vostok. It's in East Antarctica. I mean, this is probably hell, more than Greenland was during my expedition. But what we can see is that thanks to the air bubble, by simply extracting the chemistry of these air bubbles, we look at greenhouse gases, we look at methane, we look at CO2, and CO2 is of course a big driver of climate change. And so we plot CO2 with time we try to reconstruct temperature. Sometimes we can actually reconstruct temperature from the ice itself by looking at ratios of oxygen within the ice. And this helps us to get a sense of what the temperature was like at the time. So they're plotted separately, which is very important. This is what I mean. And to be able to date the ice cores, this is the third thing we have to do to date the ice. We do that through different techniques. So we do a lot of modeling by saying, okay, there's been so much snowfall, the ice is so deep in the ice sheet, the ice is about this age. But also we use a lot of things we find within the ice. Sometimes we find volcanic ashes. And by trying to reconstruct where the ashes are coming from, we know they're coming from this volcanic eruption that happened at this time in the past. So this is how we're dealing with ice cores. And I'm absolutely not an expert in ice cores. There's too much chemistry for me. But basically what we can do is plot something like this. So when the CO2 concentrations increase, you can see the response, temperatures increase as well. And this is typically when we have an interglacial period between ice ages. When CO2 concentrations decreases, temperatures plummet, they drop, and this is when you get an ice age. And so thanks to these little air bubbles and these ice cores, we've been able to see the alternation between ice ages, when we had a lot of ice on Earth, like the best time ever, and then interglacial periods when actually the ice cover on Earth was being reduced. And so it's been going on and on for quite a while, you know, these ice ages, interglacial periods, ice ages, blah, blah, blah. And basically this is where we're at the moment. So we're slightly above that now. We are at about 414 ppms of CO2, parts per million of CO2. And again, this shows you how abnormal the change in concentrations of CO2 is compared to the past. So I hope this answered the question about ice cores. All right, I will continue. Can you see penguins or polar bears there? So polar bears are in the Arctic and penguins are in Antarctica. So when we were in Greenland, we were not really thinking about polar bears because we were deep onto the ice sheet. And usually polar bears, they need to hunt seals, and seals are on the shorelines. I mean, they need the oceans to survive. So we didn't see any polar bears in Greenland, thank God for this, because we didn't have anything to protect ourselves from polar bears. Polar bears, you can see a lot of them in Svalbard though. I think Tina and Dr. Biju can definitely tell you about this. Yeah, they're definitely all over the place in Svalbard, and it makes it very complicated to do field work because you constantly have to worry about polar bears. Penguins are in Antarctica, and penguins, so we saw a lot of penguins, like so many, when we were at the station, when we were preparing for the fieldwork, but we didn't see any life when we were on the Larsen Sea Ice Shelf. We didn't see anything. I think perhaps like one bird one day, and we went crazy about this. We were so excited, but otherwise there was barely any life. I think the life was probably a few microbes here and there, nothing major. Okay, so then Sandra asks me, do we have such postgraduate courses offered by any Indian institute for physics students? So there must be. I'm not the best person to answer to that question. And I think don't hesitate to ask perhaps Dr. Tina or Dr. Biju for this. They would know more than me, but I have no doubt that there is some glaciology or snow physics courses in India, especially in the north, I think, close to the Himalayas. This is very important. And I'm glad you're keen, because this is a great course to take. Otherwise, there are plenty of courses like this in Svalbard for sure. So then clarification about one of the slides, different layers are explaining. Let me see a slide about ice cores. Oh, it must be a very one that was quite far away. So you're right. This is a very good question about. I don't know if you can read the question, but it's in the ice core, different layers are visible, and it's true. So basically, ice cores are a little bit like the rings of a tree. Oh, I think I just passed it. Are a little bit like the rings of a tree. So usually you can, especially if it's young ice, so ice that is a few hundreds of years old, you can see the difference between summer and winter. So usually, even using your own eyes, you can count the years, but eventually the ice is under so much pressure that then you will have to use a microscope to do this. And then eventually, when all the layers are kind of mushed together and you cannot really see what's happening, you use modeling to be able to do that. So then, M. Kumar, I would like to know what are the basics parameters that I used for the study, the kind of instrumental error. Yeah, I mean, good question, for sure. Especially when it comes to, I think you're referring to, I know, not necessarily to ice cores, but basically, yeah, there is instrumental error in everything that we do. No doubt about this, and we do not shy away from this. Quite the opposite. We keep on improving the precision and the accuracy of our measurements. So this is very important. When it comes to ice cores, perhaps I can talk about this. Of course, we take into account the decay of these elements into the air bubbles. This is very important. We take into account the possibility of having microbes and bacteria eating the CO2 in the air bubbles. So this is science that has been proven and verified using many different proxies. We don't use ice cores to validate ice cores. That's what I want to say. We use other proxies to validate ice cores. And this is the only way we can improve our understanding and improve and reduce our instrumental error. So that's a very good question. Thank you. From Biju, you mentioned GPR. I love GPR. Oh, yeah, that's true. Unfortunately, I do not have a radargram of, but I'll definitely send it to you. Look, I'll be writing this down. I'll send you some of the radargrams we collected, either in Svalbard or on the Larsen Sea Ice Shelf, so you can get a sense of what GPR data looks like. It's not as clear as you might think. It takes a little bit of getting used to it to read the GPR data, but basically, for example, you can see the contrast between ice and water. You can see the contrast between ice and a very large layer of sediments. You can see the contrast between ice that is very cold, very far from the freezing point, and ice that is almost melting. So this is why GPR data is so good. And also it can go through 800 meters of ice, no problem. So it's true, I should have thought about this, engineering students. I should have prepared some radargrams, but I'll send you something, I promise you. Thank you so much, Avinsha. I really appreciate it. Can we become members of this project? Thank you, Merin, for this question. So, I mean, I was in that situation for a very long time, and I was so keen to join these expeditions. And I think what really helped me to be able to travel to these places was to gain as much field experience as possible, but without going to Greenland or Antarctica. I mean, field experience could be going to the countryside. It could be going on the hills. It could be going to bigger mountains. For me, when I was able to show that I had a little bit of climbing experience, that I knew what it felt like to be cold, I knew how to set up a tent, then to the eyes of my colleagues, of my senior colleagues, they could see that I would kind of survive during these expeditions. And I learned a lot, and you learn every time, and you have to start somewhere. Also, I would really recommend you to not to hesitate to email people directly. I mean, if you see a professor that is working on cool stuff, I mean, perhaps using GPR in Greenland, do not hesitate to email them and say, hey, how could I be part of your project? I'm very interested in learning and also helping your project. I think it's super important to be proactive. When it comes to me at the moment, unfortunately, I do not have the structure to be able to take people with me in the field at the moment, but really try to email universities, try to email research labs, because believe me, they always need people to help. And when I started, I was the one carrying the backpacks, I was the one cooking, I was the one doing all the work that does not seem very exciting, but I gained a lot of experience for that. So you have to start somewhere for sure. Rijo, you said there is a documentary titled The Great Global Warming Swindle. Ooh, I do not know about this documentary actually. That the sun has a great role in climate change. Absolutely, this is completely true. I mean, the sun has been changing our climate for a very long time. When you look at ice ages and interglacial periods, this was caused by the shape of the orbit of the planet around the sun. So the sun plays a very, very big part in changing our climate. But when you look at the last 150 years, actually the sun activity cannot explain the changing climate we have at the moment. So perhaps that was 10 years ago. 10 years ago, we knew that the sun wasn't capable of creating the changing climate we have today. What is important to also keep in mind is that there is a really huge amount of interest in keeping people using fossil fuels. And I'm not talking about conspiracy theories here. I'm being very serious. There are incredible industries that want people to keep using oil, keep using coal, keep using natural gas, because it keeps the market running and it keeps making people pay for their salaries. And so for a very long time, there's been a very large effort from lobbies to try to create doubt in people's minds, to say, oh, scientists are not very sure about the current changing climate. They're not really sure that the temperatures are increasing. They're not really sure that the increase in CO2 emissions is directly related to our activities. Today, just to be clear, there is zero doubt that our activities are creating the current changing climate. And this is where we have to start. We are the biggest problem, we are the biggest solution as well. So we have to tackle this head on. But thank you, I will definitely try to take a look at this documentary. And it was probably a valid agreement 300,000 years ago, but the sun cannot explain the changing climate today. But thank you for your question, and I'll definitely try to watch the documentary. If you have a link, send it to me, please. So then Viju said, after 4 years of studies in engineering, how can these kids, you're not kids, use their skills in glacial studies? So to be honest, you probably have the best background to study glaciology. I come from a background of physical geography, and I've had huge regrets in my decision. I should have definitely gone into engineering. Because when it comes to glaciers, you have to be able to understand fluid dynamics. You have to be able to understand the physics of ice, that is this non-Newtonian material that is very complicated. You have to be able to understand how the atmosphere works, how our oceans work, how meteorology works. And I think engineering really prepares you so well. You're kind of a Swiss Army knife. You're really able to understand everything that is connected to glaciers and ice sheets. So I envy you, and I really hope that some of you will be able to get into glaciology. But also beyond that, beyond glaciology, you will be the one working, and you probably are already working on the solutions to tackle climate change. So I really appreciate that. Robin, thank you for your question. Is industrial symbiosis alone can be a great solution to combat climate change, global warming? I mean, for sure. I think there's a big part of engineering associated with industries, big industries, to tackle climate change. There are no other ways around. I mean, being able to foster energy from the sun, energy from the wind, energy from the waves, we need engineers to be able to do this. But most importantly, we need these big industries to start understanding that it is in their interest to embrace this revolution of clean energy. So yeah, we need everyone to be able to work together. We're on the same boat, so we instead of pointing fingers and saying, oh, these are the bad guys, this big industry, they're doing the wrong thing, let's work together and let's try to find solutions. So then Arundhati, you said, thank you for your question, the lakes which are formed are different layers of the ice bucket, do they refreeze? Good question, and I should have explained that a little bit better. So you can have, on the Larsen Sea Ice Shelf, when you have melt, you can have big lakes or small lakes. Typically, small lakes that are kind of like a few meters across in diameter, small lakes, they refreeze. But big lakes, like the one you saw when the little camera was going down the ice shelf, these big lakes do not refreeze. I mean, it takes actually more energy to refreeze the lake than to keep it liquid. So these lakes, they stay liquid for a very, very, very long time, which is crazy to think. Like this lake is surrounded by ice, but it's still liquid. So thank you for your question. Vanny, thank you very much. Good. So I think I've looked at most of your questions from the chat. And now, if that's okay with you, I will try to, I don't know if I can change my slides. I will try to look at the questions you sent me by email. So sorry, I think I have to stop sharing and share again because my PowerPoint is unhappy at the moment. But let me see, I have the questions right here. And I don't think I need to share the screen again to do that. So just a few seconds. I'm almost at the end of my presentation. And thank you so much for your questions. And also thank you so much for the posters you made. I really appreciate that. This is a lot of work. And so thank you. This is super kind. So I have 8 questions that were sent to me. And let me take a look at the ones I haven't answered yet. So question number 2, how is the international scientific community doing to respond to these challenges faced in the polar regions? Very good question. So what we do primarily as scientists, our work is to try to get the best available data and to publish this data, to get it peer-reviewed, to get it checked by our community, and to publish this in these journals I was telling you about earlier. But beyond that, once our papers are being published, they are basically extracted and put into an even bigger report that is called the IPCC report. IPCC stands for the Intergovernmental Panel on Climate Change. What the IPCC does is that every few years they compile a giant report that is way too giant, I think, to be of use. But they compile this giant paper of the state-of-the-art science on climate change. And then this report is communicated to policymakers, governments, decision makers. So the IPCC is kind of the link between the scientific community and decision makers. Because we do know today, if we want to face this challenge in the polar regions, if you want to tackle these challenges, we need to have the decision makers on board. We can only do so much at our levels. I mean, we can use a bike to go to work, we can try to take short showers, we can try to eat more vegetarian food, which is very good for the environment. But eventually, I mean, there's a limit to what we can do at our level. If the governments are not able to make big changes, big structural changes, it will be very difficult to tackle climate change. And the only way to do so is to educate the policymakers, the decision makers. And the IPCC is one of the many ways by which we communicate our science. At the moment, this is what I do full time, is try to be a link between the scientific community and the governments and the decision makers as well. And let me tell you, it is very frustrating. It is very difficult, but we're not giving up. We're definitely trying to hit the nail on the head, and we're doing this non-stop, and eventually I think they will give in and they will start reacting. But great question, thank you. So then how does climate change affect Arctic biodiversity in the future and present state? Oh, what a great question. And you know, I'm always sad when I see glaciers melting and glaciers retreating, but there's nothing more impactful than seeing animals or vegetation reacting to climate change. I mean, mostly animals, right? I think we can all agree. And polar bears have become kind of like the picture child of climate change. Every time we talk about climate change in the Arctic, we talk about polar bears, and they are already being affected by climate change. So what's happening is that because the Earth is warming and the Arctic is warming as well, species are migrating further and further north. And eventually there will be no further north for these species to migrate to. So this is what we're seeing. We're seeing a lot of different species of fish migrating further and further north. Some people are happy in Svalbard because there is more fish. But also that means that species that were super far north are starting to see some more competition coming. And so it is creating a lot of conflicts for animals and for vegetation as well. And it is definitely not all good news. And it's not uniform. It's good for some species, it's bad for other species. Polar bears depend on sea ice. And I don't know if you remember what I showed you about sea ice, but it is retracting very quickly year after year. And eventually there will be no sea ice left for the polar bears. So it's difficult times for the biodiversity. And basically the rate of change is faster than their rate of adaptation. So they cannot adapt fast enough to keep evolving facing this changing climate. Thank you for this question. Question 5, I hope we have enough time because I can keep going on and on and on. I think your questions are really great. So how can engineers contribute to sustainability? I think we've covered this quite a lot already, but I think what you have in your hands is absolutely priceless. You can definitely be the ones driving the change, accompanying the change, and we absolutely need engineers on board. And I've always felt super sad in Svalbard when I saw some of my students studying geology who were going to work for the oil companies. I find that very, very sad. And keep this in mind, because some of the most attractive jobs at the moment are working for oil companies, working for companies looking for oil and gas or coal. But please be the change, make the change, try to be proactive and make a positive difference. Can I continue? Yes? Okay. Yeah, it's okay. Okay, perfect. But thank you for these great questions. How can a student contribute in preserving the frozen world? Oh, wow. Very good question. How can I contribute? How can I volunteer and work in the polar regions for protecting these areas? So there is a lot you can do. There is a lot you can do. I'm a firm believer in education. And I think that with the amount of knowledge you have, which is tremendous, you can already do a lot by explaining to people what's currently happening. Not by pointing the finger, this never goes anywhere, but always by sharing the knowledge you have and be curious. Always be curious and try to understand why are some people still looking for fuel for oil these days? I mean, it is very interesting to study this, for example. So always do that. When it comes to working or volunteering in the polar regions, there are so many NGOs, so many organizations that exist. Let me try to name some. There is the Climate Action Network, there is Youth for Climate, Fridays for Future, Protect Our Winters. There are so many, and they're always looking for volunteers. And this is how I started actually in science communication. I started volunteering for an American NGO called the International Cryosphere Climate Initiative. It's a mouthful, but I volunteered with them for a year, and eventually they gave me a job, and since then I've been working with them. So volunteering has a lot of power. It can also help you to test different things. You know, if you're not happy with this NGO, you can always move to the next one. Some NGOs work a lot on biodiversity, some work a lot towards policymakers. So if I think of some more organizations, I will definitely write them down in my email. Then there is a question, what has been the most beautiful moment in your life? Which is a very touching question, and I appreciate this. To be honest, I think some of my most beautiful memories are from these expeditions. Hands down. I mean, I've had such hard moments, but beautiful moments as well. And I think by doing fieldwork, by being able to see these landscapes and working through these landscapes, you really appreciate the small things, and they really keep you humble. So I don't have one example in particular, but I've loved, even though some expeditions have been really hard, I've always learned so much and always appreciated being there, for sure. And I think that's about it, because the last question is about ice cores. So are there more questions? You can just turn on your mic or your video or both. How can you ask questions further? Drop me an email. No problem. So I'll put my email a little bit further up, I think. So go ahead if you have any questions. I know I can talk a lot, so you might be a little bit tired of hearing my voice. Tina, you don't have any questions for me?
Yeah, you should ask her.
Tina, you're muted. Oh. So I think Tina has a lot of perspectives also on climate changes, and she works on different timescales than me. But to turn on, it's at the bottom in the middle, and it's like the candle thing. It's the microphone. Yeah, you know. But I think you plugged in your earphones after, so maybe it's not looking for the right microphone. So if you disconnect your earphones and unmute yourself, perhaps, no, but I unplug it and unmute, perhaps it's going to work. I don't know. And if it doesn't, don't hate me. But I think you have to unplug your earphones, like remove them from your computer. Oh, no. Well, if you maybe someone can unmute her, no? Maybe the organizers, no? Sometimes you can do this. No. Yeah, maybe, yeah. But in the meanwhile, if you have any questions, any other questions, any things I didn't explain well, there are probably many. But I'm really envious for all of your talks you're having. You know, I might hide in a little corner one of these days and try to attend one of your many fact talks, because this is such a great initiative. And you're doing this so professionally. This is very nice. Mukul, so you sent me a question saying, with all these studies, I think it is, yeah, good question. It is easy to be cynical about the future. How do you manage to stay optimistic? I mean, for sure. I mean, every day in glaciology, every day you get a new publication. It's like, oh, these glaciers are melting faster than we thought. We're on a trajectory to higher and higher emissions every year. And to be completely fair, I think we do not have the choice. I mean, being pessimistic to me is just giving up. It's just like, you know, why should we fight? Why should we try to tackle climate change? I think we don't have the choice today. When you know that, you know, there are almost 700 million people who live on coastlines between 0 and 10 meters of elevation, and you know that Antarctica holds the equivalent to 58 meters of global sea level rise, we do not have the choice today. We do not have the choice. So I'm a very optimistic person. I always try to find a silver lining, and every sad paper I get is more motivation for me to act. So this is what I think about every day. And I hope you will also try to find some silver linings in everything that you do. But thank you for the great question. Any more questions? Go ahead. Do not be shy. Thank you, Mukul. Joby, I can see your video is on.
Hi, ma'am. Yeah, I think we are done. I don't think anybody else has anything
Okay.
to doubt. I mean,
Good.
we'll probably wait for a few seconds to see if anyone has any doubts.
Yeah, exactly. I saw that Tina probably disconnected as well. So I don't know if she's going to try to reconnect or if she's just giving up on this microphone. Have you been to India? I have been to India, actually, luckily, yeah. I've been to West Bengal for Tina is back. So I've been to West Bengal for one of our common friends' wedding, Sri Kumar. And that was back in, I'm really bad with the dates, but that was a couple of years ago. And it was incredible. And you know what? I even brought my mom with me. And she was like me, like every day, it was so extraordinary. We couldn't believe it. But India probably takes many lives to travel through. It's such a beautiful country, but so big and so many different cultures, languages, regions, landscapes. I would love to come back one day. I would love to go to the Indian Himalayas. Yeah. So that's on my bucket list. Tina, I can see that you're back and that your microphone is working.
Yeah, yeah. No, I had a technical questions, but now I think you are on the lighter side, so I'll ask you later. Is that okay? Yeah.
Oh, go ahead. No, that's fine.
No, because you showed a slide where you are drilling a borehole.
Yeah.
And you inserted this camera inside, and you found a pool, right?
Exactly.
So if I'm not wrong, you did this on ice shelf, right?
Yes, that was on ice shelf. Absolutely.
So normally, like you remember at what thickness you found the pool? Because normally below the ice shelf is the marine water, obviously, right? So is it in between the somewhere?
So basically, it wasn't very deep at all. The ice shelf was 800 meters thick.
Mm-hmm.
And underneath the ice shelf, as you said, there is this cavity, so there is the ocean.
Mm-hmm.
And the ice shelf was just a few meters down. It was like 5 or 6 meters, the ice shelf. The lake was 5 or 6 meters down. And basically, the lake forms, or the lake stops when the ice becomes too impermeable. Because you have snow, you have fun, you have ice, and the ice becomes denser and denser and denser, and eventually that little liquid water cannot go any deeper. So basically these lakes, they do not go super far, but just the fact that they are there, just the fact that they are liquid, and they are very hot. I mean, imagine it's liquid water surrounded by super cold ice. They're very hot.
Yeah.
This is really disturbing the integrity, the stability of the ice shelf. Yeah, I mean, this is insane. Nobody knew there was water in these ice shelves. Yeah.
But looking into their depth, you can guess their age, like how many years back, or 10 years, 5
I mean,
years.
they're not very old at all. The lakes, they're typically a few years old, and we know that they form at the surface of the ice shelf.
Mm-hmm.
When you get really warm winds. So they're called fun winds. And these fun winds, they can even occur in the middle of winter. And so even in the middle of winter, you have these lakes forming. Sometimes if they're big enough, they can form these huge lakes. And the lakes, they will start to like slowly and surely make their way into the ice shelf. But they're not very old for sure. Yeah.
Okay.
But as the ice shelf is extending further and further into the ocean, you have more and more of these lakes. You have like a string of lakes, basically, that have been formed within the ice shelf.
Okay.
Yeah.
Yeah, that's interesting, because I haven't seen these like pools earlier. It's just that we have seen the evidence that there was a pool, like you showed those lenses.
Yeah,
something like that, but not the real pool.
That's the mini pools. Yeah, that's the
pool in
big
yeah.
But you see, basically, what's interesting is that when it comes to glacier ice or ice shelves or ice sheets, the enemy is liquid water all the time. It's always liquid water. It's kind of the same thing, but no. And it's water against water. Yeah.
Okay. Yeah. So precipitation also has a role, right? Because of the temperature now, instead of snowfall, there will be like more precipitation. So
exactly, that's a very, very good point. And in Antarctica is a desert, so it's the most arid place on Earth. And basically, as the temperatures are slowly rising, the air masses are able to carry more humidity. So more humidity is good if you have snow. It's terrible if you get rain. And what we're seeing is that on the Antarctic Peninsula, it can rain now. It can rain in Antarctica. Yeah, not a lot, but it can rain. And that's not good. Yeah.
Okay. Yeah.
Thank you for your questions. It's pretty good.
Yeah.
Cool. Is there
butterfly effect? What is that?
The butterfly effect. So so basically that's a very good question, about the butterfly effect. If one glacier collapses somewhere, it could create like a domino effect and have consequences much further out in the world. And this is kind of what's happening. I mean, if a little glacier in Svalbard is melting, this is affecting Bangladesh. And this is kind of the butterfly effect. So definitely, this is what's currently happening already. Yeah.